Okay, example 7. So before we look into it, A is 0.005 meters squared, so that must be the area of the cable. I, which is the second moment of inertia of the beam, that must be 0.00125 meters squared. Now E for both is the same, so E is 200 times 10 to the 6 kilopascal. 1 Pascal is equal to 1 Newton per meter squared, which is also equal to 1 times 10 to the minus 3 kilonewtons per meter squared. And so 1 kilopascal is going to be equal to 1 times 10 to the 3 pascals, which means that E is equal to 2 times 10 to the 8 kilonewtons per meter squared. So from there we get EA equals 1 times 10 to the 6 kilonewtons, and then from there we get EI is going to be equal to 2.5 times 10 to the 5 kilonewtons meter squared. So now let's look at the problem. We've got a beam. One end is pinned 8 meters along. We have a cable 3 meters from the end. There's an overhang. The total length of the beam is 11 meters and 5.5 meters from here to the center of the beam. So up here we've got a cable, and that cable goes up to a point D. So we've got A, which we'll call there. We've got B, which we will say is there, and then we've got C, which is at the end, and then up there we have D. So we know that's 6 meters, and then by Pythagoras' theorem that's going to be 10 meters for the length of the cable. Along this we've got a UDL, Q, and Q is helpfully in the units. Q is in the units of 125 kilonewtons per meter. If we wanted to know the angle alpha, we could say sine of alpha is equal to sine of 36.8. I'm calculating alpha based on 6 over 10, and sine of alpha is also equal to 6 meters over 10 meters, which is equal to 0.6. So we've got so we know that sine alpha is going to be equal to 0.6. So let's calculate the total load acting on the beam. So the total load I'll call is W. 8 meters plus 3 meters, which is the total length, multiplied by Q, and that turns out to be 1375 kilonewtons. Now, in terms of the force acting, let's take out the beam again. So we're just considering with the beam, and then there's a tensile force T, which must be in tension, and it must be pulling in the direction that we've just shown. So two components to this, T sine alpha, and the horizontal component T cosine alpha. If we say the load W must be acting halfway along the beam at 5.5, so we've got W going there, and W is equal to 1375 kilonewtons. So we've got A is there, and B is the point at which it's on. So let's work out, let's just take moments about A. So we get T sine alpha times 8 meters must be equal to 1375 kilonewtons multiplied by 5.5 meters, and that gives you T sine alpha is equal to 945.3 kilonewtons, and T is equal to 945.3 kilonewtons divided by 0.6, and that works out to be 1576 kilonewtons. So we've got T sine alpha, which is the vertical component, it's 945.3 kilonewtons, and T is going to be 1576 kilonewtons. So we've almost got everything that we need. Now let's just deal with the beam again. So we've got our beam, we've got the force. Let's just plot the bending moment diagram. Let's see. So we would expect a parabolic bending moment from the end, going down like that. And then this bit here, we would expect that to come down like there and to go through here. Now, let's work out our reaction at D. So the vertical reaction at D is clearly the same force that we've applied in the tension. So that's going to be 945. So that's going to be 945.3 kilonewtons. And so the reaction at A is going to be the total force applied to the beam, 1375 minus 945.3, and that will give you 429.69 kilonewtons. So let's stick the reaction up there. 429.69 kilonewtons. And then obviously on the beam right there we're going to have a UDL, and then we would expect a bending moment distribution like there, and then that point is the point of zero moment. Let's work out the maximum value up there at B. So the moment at B is going to be equal to Q times 3 meters, since it's a 3 meter overhang. Times 3 meters over 2, and we'll get 562.5 kilonewtons. So we can work out an expression for, let's divide the beam up into two. So we'll call this bit the main beam, and then we'll call this bit here the overhang. So the equation for the real beam is would be 429.69 kilonewtons multiplied by x, taking our x coordinate from that point there for the main beam, and that needs to be minus q qx times x squared over 2 because of the UDL. So qx times, hang on a second, qx times x, now qx, so it's qx squared, or qx times x, let's just tidy it up, qx squared over 2. Now that's going to be the shape of the bending moment equation. If we set that equal to 0, so if we say bending moment is equal to 0, which would be at that point there, bending moment is equal to 0, we've got an equation to solve, and that can be solved quite easily, and we get that distance leads to x is equal to 6.85875 meters, which effectively means that if we want at that point of zero bending, it's going to be a distance of 6.875 meters from the start of the beam. And then that equation would continue. So we'll be looking later on from that equation to be running from 0 to 8 meters. And then if we had a look at the overhang later on, we might find, well, actually, if we wanted to find the maximum value down there, that's really the point where the shear force diagram is going to be equal to 0. So that value can be calculated saying 429.69 minus Q times X, and if you set that equal to 0, that would be the point of zero shear. So we've got the reaction minus the load caused by the UDO, and set that equal to 0, and then we will get that X is equal to 3.438 meters. So we're effectively saying that the maximum value there is going to occur when 3.438 meters. So we've set up some geometry for the problem. Now, if we wanted to get the equation for this bit here of the overhang, so again we would set up another system later on, starting from x is equal to 0 up to x is equal to 3 meters, to represent the overhang, and the equation for that one, the bending moment, is going to be equal to this 562.5 kilonewton meters. So there should be a there, and that from there should be subtracted Q x squared over 2 to deal with the UDL acting over the overhang. So there are a number of ways in which we can solve this problem later on. So you've looked at Appendix 1, Appendix 2 and Appendix 3 of the course notes. What probably seems the easiest thing to do here is just to integrate the thing and leave things algebraic. So all those things that we've calculated would be of use. The only thing that won't be of use probably will be this x equals 3.438 meters. That's okay. If you did want to use Appendix 2 later on, you could probably make use of that value and get the parabolas to work each other out. But I think in this case here we'll get the most accurate solution by doing the integration.